LeetCode problem 1639, titled Number of Ways to Form a Target String Given a Dictionary. So we're given a list of strings of the same length, words, and a string target. And our task is to form target using the given words under the following rules. So target should be formed from left to right, and to form the ith character, which is again 0 indexed of target, we can choose the kth character of the jth string in words if and only if target at index I is equal to words at index j index k. And once we use the kth character of the jth string of words, we can no longer use the xth character of any string in words, where x is going to be less than or equal to k. And so, in other words, all the characters to the left of or at the index k would become unusable for every string. And we need to simply repeat this process until we actually form the string target. So notice that you can use multiple characters from the same string in words, provided that the conditions above these operations or criteria are actually met. And we need to simply return the number of ways to form target from words, but since the answer may be too large, we have to return it modded or modulo by 10 to the 9th power plus 7. I think that's just a really large prime number, but correct me if I am wrong. So in example 1, we have our input array words to be the following. We have ACCA, BBBB, and CACA. It's literally just a list of strings. And in this case, our target string is going to be ABA. And the reason why we output 6 is because that's the number of ways we can actually form target from the words input, right? And they actually list down the 6 different ways we can actually form the target. So from ABA, we can get index 0, which is A, and then index 1 of BBBB, which is B, and then index 3 of CACA, and we get A, and this B, and this A. Another way we could get ABA from the words in our input string words is going to be index 0A, the second index BBBB, and index 3 of A. That still works. We're still maintaining the relative order of the indices we choose the words from, and also we still form the word ABA. Another alternative we can actually make to actually get or rather form the input string ABA is get index 0 ACCA, index 1 BBBB, and index 3 ACCA. Okay? And they really just, these are you can probably, this is pretty self-explanatory here. They're just listing the other 3 examples, or rather the other 3 methods that we can get different indices from our input string words to actually form the target, actually just taking a letter from each word. And an example, the reason why we return 6 is because, again, that's the number of unique ways we can select indices, or rather letters, from different words to form the target, as we actually maintain these rules, maintaining it formed from left to right, and so on and so forth. So in example 2, we have our input string words to be ABBA and BAAB, and our target to be BAB. In this case, there's only 4 ways to form the target from our input string list of words, and in this case, the 4 ways to actually form the target, which is actually BAB, would be first selecting index 0 from this word right here to get B, and then index 1 from the same word to get A, and then index 2 from the first word, ABBA, to get BAB, which, believe it or not, is our target string. That's one unique way to form it. Another way we can get BAB would be getting index 0 from BAAB, index 1 from BAAB, and then index 3 from BAAB. We're not even using this ABBA, we're only using letters, or rather indices, from the second word, while actually maintaining the relative order of the indices we choose them from. In BAB, another way to get it is first selecting index 0 from the second word, and then index 2 from the second word, and then finally the index 3 from the second word. That still is a valid unique solution to form BAB, and this is the final method we can do it. So pretty self-explanatory here, as you can see in the examples as well. And for the constraints, the length of our input words is never going to exceed 1,000 and go less than 1, of course. And words at I, for any length at that index, is going to be also within 1,000. And all the strings and words are actually guaranteed to have the same length. where that length of the target word is also going to be less than or equal to 1,000. And this is really just to avoid any base or rather edge cases here where we don't have valid inputs or invalid characters. We know, or rather we're guaranteed, that words.i and target every single letter is going to contain only be a lowercase English letter. So with these examples, problem statement, and constraints out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what is one key observation that we can really make for this problem to actually really efficiently solve it? Well, really, this problem doesn't actually require us to actually rearrange the strings and words, right? Really, instead of that, we really just have to pre-compute the frequency of each character in every single column. And that's simply just going to really make our solution more efficient and really just save us a lot of time. And this is actually going to be a classic problem for dynamic programming, right? And the reason why is because dp at index I, index j, the extra 2D array that we store, that's going to be the number of ways to form the substring target I from index I till the end using the first j columns of the words, right? And for context, to just comment this out, dp at I at j, I'll try to keep this as simplified but concise as possible as well. It's going to be number of ways to form substring. Let me find the thing. Okay, I think it's like this. Yeah, should be like this. And by the way, I colon is really just list slicing in Python. It's from index I till the end of the array because we don't have that second parameter after the colon. So that's what the default is going to be. And this is going to be that substring using the first j columns of words. And yeah, okay, awesome. So just for a little context to look up at this and reference this as we're actually coding up this solution. Right? And of course, the final answer that we're going to eventually have to return is going to be stored in dp index 0, index 0, right? Basically, that's going to be the leftmost index, which is going to represent the number of ways to form the entire target string, actually starting from the first column, right? And for the actual pre-computing part where we actually pre-compute the frequencies, before we actually even start filling up and populating our DP table that we initialize, we have to actually create a frequency table where frequency at index C, index J is going to represent the number of times character C appears in column J. And so let me just actually comment that out as well. So I'll just call it freak. Let me actually comment this out as well. So freak. This is just going to be a hash table for our frequency references, right? So frequency at index C, index J. This is simply going to be the number of times character C appears in column J. Okay, I just realized I butchered the spelling of column. I think it's like this. It might be with two L's. I'm just going to assume it's only one L in column J. Okay. And effectively, once we're actually done pre-computing these frequencies for the actual recursive transition part of this solution, if we don't actually use the current column, well, the number of ways remains the same. It's going to be the same as dp at I at j plus 1. However, if we do actually use the current column and the character does actually match target at index I, well then we have to add that frequency at target at index ij times dp at I plus 1 j plus 1 to our result. So it might not make the most sense. I'll explain it as we code it up as well, just so it really just sticks in your mind and you actually understand how we actually solve this problem. So before I do anything, let me just declare my mod, right? Or my modulus. So I'm literally just going to call it mod in uppercase, and I'm going to initialize it to 10 to the 9th power plus 7. Again, I think it's just a really large prime number. And really the only point of this is just to mod our result by this so that it doesn't actually go too large, right? Because the answer may be too large and it may be too big of an integer, and so we're just going to mod it by 7, okay? That really is just going to be the actual like modular arithmetic operations to prevent integer overflow, right? If you guys don't know what integer overflow is, don't worry about that. It's fine. Okay, so now let's actually start pre-computing our character frequencies, okay? So I'm going to set n to be equal to the length of words at index 0, basically the first word in our input string words. And I'm actually going to initialize my frequency hash table. It's simply going to be a hash map in an array in the range, or rather with dimensions, of n. And this is just a nice little neat way to initialize according dimensions of n for data structures like hash maps and arrays, right? So again, what these two lines really do is here, n is simply going to be the number of columns in the words list, right? And the reason why I set it at words at 0 is no really big reason. I could have set it at words at 1 or 2 as well. It's just we're guaranteed that we're going to have at least one word, and so I just set it to words at 0. And we know that n is going to be the length, or rather the number of columns in the words list, because all the strings are actually guaranteed to have the same length, right? And this frequency, I just called it freak, this is actually going to be a list of dictionaries or hash maps in Python, right? And we're simply going to use it to store the frequency of each character for every column, right? So now let's actually kind of build up that frequency. So for every word in our words, so for every word in the words input list strings, and for every word, for every character and index in the enumerate of the current word, with some nested loops here to effectively iterate over every single word and its corresponding character and indice in our input string list of words. Now, if the current character, C, in fact, sorry, there should be J in character, not just C. If the current character char, if it's not in the frequency table already, or rather frequency table at index J, meaning at this column, well, then we want to update it. So frequency at J, rather at char, is going to be equal to 0, actually initializing its key in the hash map if it's not already in the hash map. And effectively, in every iteration that we do this, if it already is in the hash map, well then great, we'll just want to increment its frequency by 1. So frequency at J at char, oops, keyboard's being a little bit funky right now, at char plus equals 1. We're really just incrementing or updating its frequency by 1, okay? So basically, what we're doing here is just for every word in our words, again, and then for every J and then character, J is the index of our word, enumerating through it. Basically, we're simply going to count the occurrences of each character and then store them in the frequency table, updating their frequencies accordingly. We update its frequency by 1 when we see it, and if it's not in the frequency, well, then we actually want to initialize its key in the hash map or in the dictionary, right? So now let's actually initialize our DP table now that we're done populating our frequency table. So I'm quickly going to grab the length of our target. So I'm just going to store that in n. That's simply the number of characters in our target string. And I'm going to now initialize my DP array, similar to how I initialized my frequency hash map, right? And how this is going to actually work is it's going to be, again, zeros with dimensions or times n plus 1. But this is only 1D. We want this to be a 2D DP table. So we're going to times it by n plus 1 in the range, so that number of times, of n plus 1. This is how we kind of initialize 2D tables, right? 2D arrays, right? And for our base case here in this DP table, we know that DP at mn is simply going to have a value of 1, right? And before we actually get into that, first of all, m is simply going to be the length of our target string for easier initialization, as you can see here. And this 2D DP table is going to have size m plus 1 by n plus 1, and it's going to be initialized to all zeros, right? And this base case for this DP table is going to be DP at mn, and that's simply going to represent exactly one way to form an empty substring of target, right? And that's going to be from the last column onward. So now this is where the chunk of the code actually works, populating or filling out our DP table before actually returning its result. So first of all, let's actually fill out this DP table and iterate backwards through the target and words column. So basically, for I in the range, and this is how you iterate backwards in Python. It's going to be m minus 1. Minus 1, we go up till -1 exclusive, or basically 0. And we're decrementing by 1, or incrementing by +1 at each iteration. And for in this nested loops, for j in the range, for every I in the range of n minus 1, -1, -1. Very similar logic here, starting from n minus 1, decrementing by 1 each time, and going up until 0 inclusive or -1 inclusive for the index. We want to first set dp at ij to simply be dp at I j plus 1, like we talked about before. And once we do that, well, we want to actually check, well, is I actually less than m? And is target at I, is it actually in our frequency at that column j? Well, if it is, well, then we want to set dp at I at j, and then increment its value or update its value by frequency at j target at I. I'm sorry, I butchered the, what is that? What do we call that? The parentheses for this, or rather the brackets. There should be target at I. So frequency at j at target at index I, and this is the kind of formula we talked about, at d times dp at I plus 1, j plus 1. And once we've done that, well, then we want to actually mod it by the result, because that's literally what the problem is asking us to do. Because, again, integer overflow. We don't want to actually have too large of an answer. So we want to then set dp at ij and simply mod it by that mod that we initialized. So, I forgot my equal sign. So mod equals. This is also an operation, by the way, guys, if you didn't know about that. It's pretty rarely used. But anyways, what does all of this big chunk of code really do? Well, basically, again, on lines 16 and 17, we're literally just iterating backwards through target and words columns to actually fill out this dp table, right, for every index I and j in that range. And what this dp at ij is equal to dp at ij plus 1 does, it simply just handles the case where we skip the current column as our current decision, right? That's what we talked about before. But if the current character in target, if it actually matches a character in that specific column, well, then we want to add the number of ways to form the rest of the target string using the remaining columns, right? And don't forget to actually take that result and just mod it by mod, right? That's really not too important. That's exactly just what the problem asks. And effectively, once we're done populating this dp table for every index I and j in this 2D array, we just want to return where the solution is stored. That's going to be at dp at 0, 0. The reason why is because that's going to contain the total number of ways to form the target string, right? And again, that's the reason why is because it's, again, going to represent the number of ways to form the entire target string starting from the first column. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So again, for a quick high-level rundown of how this code actually works, it's not too bad, as you can see. Really, we're first pre-computing the frequency of characters in each column to basically just efficiently calculate the number of ways to form the target string using that dp table dp, right? And by iterating backwards through both the target input and the columns, we're making sure that every single possible substring and column combination is going to be actually checked. And this modular arithmetic operation really just ensures that we don't actually have an integer overflow, our result isn't too large, and it stays within bounds. That's exactly really what the mod actually does. So for the time complexity of this solution, this is going to be a big O of n solution. The reason why is because actually pre-computing frequencies is going to take big O of n, where n is simply going to be the number of columns, and the length of the words is the number of strings, and filling out that dp table is actually basically going to have m, where m is the length of the target string. So as you can see, the overall time complexity is just going to be big O of n times n, right? Or nm. N is again the number of columns, and the length of the words is really just m. And then for the memory complexity is also going to be big O of n times n. Why is that? Well, the frequency table actually requires space for storing character frequencies, but also more importantly, this dp table also requires extra memory. It's going to literally have size simplified n by n, because that's how we initialize it, with dimensions m by n. Right, so the overall time and space complexity are both going to be big O of n times n. Again, because we have to pre-compute the frequencies, right, and we also have to fill out the dp table, and m is going to be the length of our input string target. And again, the frequency table is actually going to require extra space for storing the character frequencies, and the dp table also requires space because it's literally having dimensions simplified of m by n. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.